Ja, maar dat lukt soms.
Maar het probleem is, je moet heel de boeken op het station ging nog een badje halen. Als ik het gewoon niet vergeten heb, dan word ik altijd een beetje moe.
Ja, ik krijg een beetje.
Is alle verven afgekomen of niet? Ja, ja. Nou, bij mij is het focus goed niet opgekomen. Oh, het is ook goed. Ik heb. Oh, dat is het best wel. En ik had het speciaal met die. Ja, ik was met de hele avond niks, ik kwam thuis. Ik weet niet, maar op het station. Maar dat is net oké. Maar ik dacht wel, hoe dan? Maar ja, ook, jij ging wel lekker door. Zoals ik het hard. Ja, hey, man, niet zo jij. Ja, dan ben je weer kwijt.
Okay, there's a lot of echo on the Zoom. People have it on here in this room.
Recording, do you?
I think I should be the only one who has the speakers on. Well, I'm turning them off now. Okay.
Yeah.
And,
can I make one remark?
Yeah.
Before you start, I've posted the assignment. You may or may have not seen it. So again, to repeat, the idea is that you can make this assignment either alone or in a group of, let's say, up to 3 people. Of course, if you make the group, you will get the same rate. I've now put a due deadline for next week Friday on it, but I'm flexible about it. Just do something. So my recommendation would be to do it in a week. If it doesn't work for some reason, then please let me know, and then we'll figure something out. So that is that. You will have. So this is the first of 3 assignments that you can either make in groups or make alone. And then there will be a final examination that you mandatorily have to do alone, because that will be the true individual adjustment, and also that you will have to pass. That's what. So if anything is unclear about that, or if you have any questions, so when you're working on the assignment, if you have any questions, do feel free to contact. It is not. It is something that I want you to learn and to do, and not already something that. So please, if there's anything unclear.
okay. Last week I forgot to hand out my question on OCT, so I'm going to do that today. He will have time during these coming 4 hours to start on it, and then I think at some point I will give a hint because I think most of you will get stuck, which is fine. But in the end, you know, it's a very nice exercise. It deals with a lot of the things about interference and noises amplification and fields and how fields split compared to intensity. So I think it's a very instructive exercise, and I don't expect you to be able to make it, but with my help, you should be, and you should learn a lot from the exercise. That's the goal. Okay, so we'll do that later. But for right now, we start with our lecture on Raman scattering and coherent anti-Stokes Raman scattering. So Raman scattering is a very interesting process because it gives extremely detailed information on molecules by examining the vibrations inside molecules. The downside, as you will see, is that it's a very insensitive technique. So you need a lot of power to excite these molecules to see these Raman signals, or you need to integrate the signal for a very long time. But it's the most specific information that you can get from a molecule without labeling it in any way. Really, Raman spectroscopy as a technique has taken off with the invention of the laser. Before the laser, there were no light sources that were powerful enough to excite molecules. You had sunlight, helium neon, arc lamps. But with the laser, you could create a really coherent beam that you could focus into a very small spot to reach the intensities that your Raman signals were observable. So along the way, I have to deal with standard scattering too. So that is basically what I'm going to start with. How does scattering work and how is it different from Raman scattering? How then do you analyze Raman scattering? What happens in the process? Why is a molecule Raman active and how? And then we'll get more to the applications. But my hope is that you will get a deeper understanding of the process itself. So, you know, when you encounter it in the future, you know at least the basics and how they work, how it works. So the Raman process is an inelastic scattering process. What happens is you send light into the molecule and it's converted to a photon of a different wavelength. And that means that the molecule has to absorb and re-emit energy. And that is an inelastic process. Part of the energy remains in the molecule. That is different from the standard scattering process that Boer has, I think, extensively dealt with. That is, you send photons into tissue or light into tissue, and it scatters around, and at some point it comes out of the tissue. But it has the same wavelength. So let's take a deeper look at the scattering process itself, because what happens when an electromagnetic wave interacts with, and let's keep it simple, with an atom. When the atom has an electron cloud around it, and the electromagnetic wave starts to force that electron cloud into an oscillation. So you have the nucleus of the atom, around it your electron cloud, the electromagnetic wave comes in, and it starts to oscillate that cloud, which means that you have created an oscillating dipole moment. And as you know, a moving charge generates an electromagnetic wave. And that's exactly what happens. That moving electron cloud is a source of secondary radiation that is emitted by the atom. So if you would show that in a very simplified diagram or a drawing, you have your electromagnetic wave. At this location, you have your atoms, electron cloud around it. The electron cloud starts to oscillate and becomes a source of secondary radiation. If I would look at it from the top, then this is my incident wave. Of course, only a very small fraction of the light that is incident is scattered. So I have a strong outgoing beam, and then we get basically a spherical wave, a spherical scattered wave coming out of this atom. due to the motion of the electron cloud. Okay. So that was the world as it was in 1923. And then three theoretical physicists, Schmeckel, Kramer, and Heisenberg. And yeah.
If I understand correctly, photons formed because of the dipole generation. So why is it called scattering?
Because the scatter is that we generate an electromagnetic wave that is now different, that is now propagating in different directions.
Is there an incident photon that can change the direction?
Well, for the scattering process, the photon picture again is problematic. Because if you look at it from a single photon point of view, then it either travels through or it's reflected in another direction. That is not compatible with the wave picture that we have of an electromagnetic wave starting to oscillate an electron cloud and then generated in secondary wave from it. So I think for the scattering process, we should look at it in the wave nature of light. Actually, I mean, the photon picture is just to get an expression for the probability distribution. If you look at the electromagnetic wave, say, let's go back to quantum mechanics, the square of your field is your probability distribution. That's likelihood to measure a photon at a certain location. That helps. Okay, so, but we use the wave picture here. That's your question, clear? Okay. Where was I? Oh yeah. So we had the three physicists that postulated that this photon scattering could also occur in an inelastic way, where energy was exchanged with the molecule, and this could involve a change of one of the molecule's quantum states. But at that point, there was no mention of vibration. So at that point, it was just the concept of these theorists that it should be possible to change the internal energy state of a molecule, the quantum state of the molecule, and that there should be a possibility of energy exchange. Only later was that identified as the vibration levels of the molecule. Okay, so the Indian physicist Raman attended the conferences in Europe and was fascinated by the blue colors of the Mediterranean in glaciers. And back in India, he started a research group to study scattering of light. Because the fact that this looks blue and this effect of light on ice, it's all has to do with the scattering that determines the color and what you see here. Oh, that's fast. Okay, so in 1930, he already received a Nobel Prize in physics for his discovery of the Raman effect, and that's the effect that was named after him. And it was indeed very fast after the publication of the first paper. I think this is the paper, 1928, and so 2 years later already the Nobel Prize in physics. So what is the effect that happens in Raman scattering? We have a laser beam of a certain wavelength. We have a molecule consisting of, let's say, 2 atoms that are bound together. And then what happens is that the photon is absorbed. That creates a vibration in the molecule. And a new photon is emitted with a longer wavelength, where the energy difference of the emitted photon versus the absorbed photon is the energy that is absorbed in the vibration of the molecule. Okay, so you can study this, and you can take chloroform CCl4, that's a carbon with 4 chloride atoms around it, and you can look at, you can excite the gas with a laser, and then look at, with a spectrometer, at all the emitted wavelengths from this. Okay, and then you have the center band, we call it the Rayleigh band, but this is the elastically scattered light. That is where there's no energy exchange. So this is the center wavelength, this is the excitation wavelength of the laser that is also scattered and emitted. So we detect that, and it's the, I mean, it's a millions of times stronger than the Raman signal, so this is a really huge peak. I'm going to show the peak here. And then around it, you can see that there are different lines. And the interesting thing is that you can observe lines at a longer wavelength, but you also can observe lines at a shorter wavelength. And has anybody get an idea of what these lines at the shorter wavelength could be? I mean, the longer wavelength is the process I explained, right? Where you have the molecules in rest, it absorbs a photon, it starts to vibrate, and it emits a photon of a lower wavelength. Here, when I look at this gas, I apparently also get photons out of this gas where the wavelength is shorter.
Because we have vibrations, but you also have rotations, like different kinds of movements in the molecule.
Yes, but if you excite these motions, the rotations and the vibrations, what will happen with the scattered light? If you just look at it from an energy picture, and you have to conserve the energy. So if the molecule is not rotating, and you bring it in a rotating motion, what will happen with the scattered photon? Will it get, but it excites the molecule. Yeah, lower energy. Yeah, so rotation or vibration doesn't explain why it gets photons of a shorter wavelength. But what does explain it? Yeah. Very nice idea, thanks, but no. Good thinking, good thinking. That's how you could get to a higher energy level, right? Look at it look at it from this way. The photon, the light apparently has to pick up energy in the scattering process to emit a photon of a shorter wavelength. So where can it get that energy from? From the nucleus? But, from the
electrons, right?
From the electrons.
Yeah.
Yeah.
It's possible to leave the atom. It's already in a higher energy state, and then it gets like.
Yes.
Yeah.
If it already is in a vibrational state, you can excite it down into the ground state, and then the photon picks it up. So you can get photons of a shorter wavelength because the molecule is already excited or already vibrating. And how do you think a gas can pick up vibrational motion? What kind of constant does describe? It's not in my slide. Just
Increasing the pressure.
what?
Increasing the pressure.
Pressure, yes. What is another very common thing to excite the gas? Temperature. Yes. And so if you have a molecule that has, let's say, excited states, and the molecule is not at 0 temperature, will these excited states be populated? No clue. Yes. Okay, I will give you the answer. You can have a thermal excitation of the vibration levels. Right? So if you cool the gas down to 0 Kelvin, and all molecules are in the ground state, there's nothing vibrating. If you start warming it up, that means warming up the gas means it starts to move around, and the molecules have a velocity. But in with that velocity, these molecules will collide with one another. And in the collision process, you can imagine that you will also excite vibrations in the molecules. So basically, temperature already will excite vibrational levels in the molecule. So when we look at this spectrum of chloroform, we see here the central peak We see here these peaks for the longer wavelength, where we have excited vibrational levels in the molecule. And we see here the lines where the laser light has picked up energy from the molecule and has excited it down to the ground. And the interesting thing is that, of course, the larger the distance from the excitation wavelength, the more energy the molecule has, the laser has picked up in the scattering process. So if you look at the energy difference between these two lines, that's the energy level of the molecule. And you also probably still understand that the larger the energy of the vibrational states, the less likely it is that it's excited by temperature. The energy levels of a molecule that are excited by temperature depend on Boltzmann's constant. So if you look at this difference between this line here and here, you see it's a large difference. It's unlikely to be populated by temperature, and that's why the line is so small compared to over here. We'll get to more details of that later. But I mean, to give you an idea, it means that with Raman spectroscopy, you can expect the temperature of the molecule you're looking at through these processes. Okay, so if you then look at the evolution of Raman spectroscopy, since it was discovered in 1928 to 1960, not much happened. But then in 1960, with the invention of the laser, this research field really took off, because now all of a sudden you were able to study not only the simplest molecules like the chloroform that I just showed you, but more complex molecules that had even lower cross sections for the scattering process. And then other big steps in Raman spectroscopy were made with the two main contributors are Fourier transform spectroscopy, and that was a method of very sensitively measuring wavelength differences through interferometry. Basically, Fourier transform spectroscopy is an OCT system, or you can say an OCT system is a Fourier transform spectroscopy system. They're very similar, microsync interferometers. And the advancements with chart-coupled devices, CCDs, that these are the chips that are used in your cameras right now. In the 80s, before the 80s, we were using photographic film, but with the invention of the charge-coupled detectors devices, we could integrate photon signals on a chip and accumulate it for long times to get the good signal-to-noise ratios. So CCDs were a very important step. Also, of course, computers and development of lasers in the near infrared. And the first laser was a ruby laser, that was a red laser. Lasers were developed mainly visible in the beginning, and only later came the near infrared lasers. And then with all these developments in the 1990s, it was applied more and more to biomedical applications. Its big benefit being that you could investigate a molecule or get a fingerprint or a signature from a molecule without using any labels. Okay. So vibrational spectroscopy. In principle, a molecule with n atoms can have 3n-6 vibrations, and that's actually 3n-5 for linear molecules. You can see that the number of vibrations that the molecule has increases significantly with the number of atoms the molecule is consisting of. And you can see that with all these vibrational levels, it is quickly possible to create a unique fingerprint of a molecule in terms of its Raman spectrum. And as I already explained, that sometimes the spectrum also contains information in the local environment. I have given you the example of temperature, but also crystallization form, redox state, that's the surrounding of the molecule, can affect these vibrational levels. And so there are two important techniques to record these vibrational spectra. One is direct infrared absorption spectroscopy, which means that you use a laser and the wavelength of the laser matches exactly the energy of the vibrational level. So the photon is absorbed by the molecule and you directly excite the vibration of the molecule, or Raman spectroscopy. So let's go over these two processes. So we have two processes. We have an infrared absorption and we have a Raman active vibration or Raman active scattering. If we have a process where only the electron cloud is distorted, we get our elastic or Rayleigh scattering, the process that I started my explanation with. If there's nuclear motion induced, there's energy transfer from or to the photon, and you get inelastic scattering, and then vibrational levels are involved. And vibrations that cause a change in the dipole of the molecule are IR active, and vibrations that cause a change in polarizability of the electron cloud around the molecule are Raman active. So I will go into detail into these two effects. What is a change in dipole and what is a change in polarizability? So as an example, we're going to look at carbon dioxide. Carbon dioxide has an asymmetric stretch vibration that is infrared active, and it has a symmetric stretch that is Raman active. So let's take a look at this. So this is our carbon dioxide molecule, and as you can see, there are three different vibrations depicted in the top row. If you look at this one here, it is the carbon atom in the center. You have your oxygens to the side, and then they oscillate. The two oxygens oscillate like this, and the carbon stays in the same position in the center. So that's our first vibration that we have here. The second vibration that is depicted here is where the two oxygens stay stationary, but the carbon atom in between oscillates in its position. And then the third vibration that is shown here is, again, the two oxygens are in their stationary position, but the carbon in between oscillates perpendicular to the axis that connects the two oxygens. So here we have our three vibrational modes of a carbon dioxide molecule. And so let's look at the dipole moment. So the dipole moment is a molecule of the dipole moment of a molecule expresses how the charge is distributed over the whole molecule. And if there's a dipole moment, that means that the charge is asymmetrically distributed, that there is a net electric field in the molecule. If you look at this picture here, where you have the carbon that needs 2 electrons and the oxygens that have 2 excess electrons in their last orbit, so they share those, and these electrons are as in a cloud moving over around this molecule. And so if you look at this dipole moment of the molecule, the dipole moment does not change with this vibration.
What does the mu and the q stand for?
The dipole moment and this is dipole moment, yeah. And this here is polarizability. Mu dq with the displacement of the vibration. There's no change in the dipole moment, but there is a change in the polarizability. So if you now look at this picture, you can see that the carbon in the center that needs 2 electrons, and in a way it's positively charged. If that carbon starts to move back and forth, that will lead to a change in the dipole moment of that molecule. If the carbon moves to the left here, then this side of the molecule becomes positively charged and the other side negatively charged. In the center, it's neutral, and then it moves to the other side. Then this side of the molecule becomes positively charged. So you can see now that with the vibration of the carbon, you change the dipole moment of the molecule. And if you then look at the last picture here, the same, we have the carbon here, and now it oscillates. The carbon atom is positive, so you create a positive electric field in the molecule, so it has a dipole moment, neutral dipole moment the other side. Again, the vibration where you change the dipole moment. Okay, so then let's take a look at the polarizability. So what does polarizability mean? Basically, polarizability means the ability to pull the electron cloud around the molecule out of position. And so you can imagine if you have electrons that are very tightly bound to the molecule, it takes a very strong electric field to displace them. Then the polarizability is low. If you have electrons around the molecule that can move more freely, and then you put that molecule in an electrical field, you can pull the electrons further away from their equilibrium position, creating a larger dipole moment. So that means that molecule is more polarized. So polarizability, in a way, is the ability to pull the electron clouds or electrons away from their stationary or ground state position due to an electric field. And if you then look at these molecules, and you can imagine that for this vibration, where the oxygens are moving towards the carbon and moving away, that you basically change the size of the construction that pulls on all these electrons that are moving around. And so by this vibration itself, you change the polarizability of this molecule. If you look at this vibration, you can see that the molecule more or less remains of the same size, also not leading to a change in the polarizability, and the same holds for this vibration. So we basically, yeah. You increase the polarizability. Yeah, because the idea is that if you increase the distance to these electrons, then it's easier to pull them away.
What's with the drops?
Yeah, that's a good one, because I don't know. Yeah, which means indicate that for this position, the electron cloud is tighter to the atoms, which means that it would be harder to pull them away. And then in this configuration, where the molecule is larger, the electron cloud most likely moves with the atom cores, and it would be easier to polarize it. Yeah.
So by definition, atoms that have more electrons are more polarized.
That seems a logical conclusion, but I'm not certain, so I'm not going to confirm it.
And it's possible to excite the molecule if you insert enough energy or pull hard enough so that the electron cloud actually gives one electron.
So if you mean if you ionize it,
yeah,
then you go into like extremely strong electromagnetic fields, and then you're getting out of what we call linear regime of the response.
Yeah.
Okay. So we're going to do a little math, and it's a classical math for Raman spectroscopy. But the nice thing that out of this classical approach to Raman spectrum, you also get the anti-Stokes scattering light, or the one where the photon actually picks up energy in the scattering process. So let's take an electric field that oscillates with an incident frequency. Okay, and then put some mess fold here. Okay. Ui. Oh no, it's not that. Ui. So we have an incident field EI that has an amplitude E0 and it oscillates with cosine of 2 times pi times mu I times t. And it induces a molecular electric dipole given by P, and that dipole moment P is given by the polarizability of the molecule, how easy is it to pull the electrons out of their equilibrium position, times the strength of the electrical field. So if this seems logical, that the easier the polarizability and proportional to the strength is the dipole moment of the molecule that you create. What is proportional to the molecular polarizability? It's the ease with which the electron cloud around the molecule can be distorted. And so this principle barely. So alpha, the polarizability, we can describe as a standard polarizability of the molecule in rest, plus a term that gives the displacement of the nuclei of the molecule, R minus R0, where R0 is the equilibrium position of an atom in the molecule, multiplied by the polarizability divided by the change in the distance. So basically, this is a Taylor expansion of alpha around its equilibrium position R0. And then we can write that the way with how far are these atoms pulled out of their equilibrium position, R minus R0, where R0 is the rest position, we can call that Q. Okay. So the polarization results in a nuclear displacement. So the bond length oscillates at the vibrational frequency. So Q, which is this, if you go back, Q is basically R minus R0, or the displacement out of the equilibrium position. This Q we can describe as a Q0 amplitude times a cosine of 2 pi mu RT, where mu R is now the vibration frequency of the molecule. Basically, we describe now the vibration in the molecule. Okay, and with that, we have an expression for Q now. So if you look now at the polarizability, which we originally wrote as a Taylor expansion around the equilibrium position of the atoms in the molecule, that polarizability is the best polarizability times out the derivative of the polarizability with the displacement multiplied now with this displacement. And this term here is just this one here. So what we get now is a polarizability that becomes a function of the frequency vibration of the molecule. Okay, so if we insert now this polarizability in our expression for the dipole moment, that was the very first thing we did here. The dipole moment is polarizability times the incident electrical field. If you do that now, dipole moment times is polarizability times incident field, and we get here the okay, should I write that out? I have time, I think. So it's alpha 0 times E0 cosine 2 pi mu IT. Yeah, so this is that what I just wrote out is this alpha multiplied with the electrical field E is E naught cosine 2 pi mu IT. And when I do that, I get here a product of the oscillation of the vibration of the molecule multiplied with the frequency of the electromagnetic field, right? And the product of two cosines. I forgot to write cosine. Cosine. So I get the product of two cosines. I can write it as a sum and a difference of these frequencies, and that is done here. So I get the sum frequency and I get the difference frequency of the two of the incident field and the Raman vibration. And with that, and this is my dipole moment. So my dipole moment is basically oscillating, which means that there are charges oscillating, which means that it's generating radiation. So what I've written now is basically what kind of radiation is emitted by the molecule in this process. Well, the first radiation is my original incident frequency, so that is my elastically scattered field. And then I get here radiation that's actually the sum of my incident field and my molecular vibration. And the second or the third field that's emitted by the molecule is my incident frequency minus the vibration of the molecule. And what I've shown here with this very simple derivation is this is my Stokes scattered light. This is the photon of a lower energy emitted by the molecule. And this here is the photon with a higher energy emitted by the molecule. And so we have our anti-Stokes and we have our Stokes photons from this very simple description of the scattering process. Then if you look at these molecular, oops, it goes forward too fast. And if you look then at these molecular vibrations and we want to have an estimate of what is now the frequency of this vibration of the molecule, we can look at the masses of the atoms. If you just look at springs that are together, that masses that are connected with springs, and what are the vibrational frequencies of this, and then you can derive that it's the spring constant multiplied by the sum of the masses divided by the product of the masses and the square root of that. That is the frequency of the vibration in hertz. So if you then look at this, at these frequencies, then we can see. Oh wait, we go to Jablonski diagram. This one, there was something else. Oh yeah, that what we get then is that if we have two light atoms, the vibrations are faster, more energetic, and if we have heavier atoms, then the vibrations are slower. That derives from this formula. Okay. So in terms of in general, you would like to show processes and transitions in energy in diagrams where I can give you an example, right? If I have a guitar and I sing at the same note as one of the strings of the guitar, that string will start to vibrate. So I hit the resonant frequency of the guitar string with my voice, with the sound vibrations of my voice. And so you can excite the guitar string easier if you sing at the same pitch. I can sing at different tone heights, and actually the guitar string will also start to vibrate a tiny bit, but not as strong as when I hit it exactly on what resonance. And so you have these energy transitions that are more like the same thing happens in the molecule. If you have your molecule and you hit it with the exact energy that it needs for going from the ground state to the vibration state, then the likelihood of that transition taking place is much higher than if you're not at that resonant frequency. And so it is often important then to describe your energy levels in your molecule. And you can do that, these are Jablonski diagrams. It describes the electronic and the vibrational states in the molecule. So basically, these are the energy levels of the molecule, and based on and this is an energy axis, and based on the difference between these two lines, that's the energy that you would need to excite the molecule from one state to the other. Okay. The funny thing in this Raman process is that you come in with a photon that has a significant energy, and then the molecule picks up a vibration. It emits the original photon at a slightly longer wavelength, so it eats off a tiny bit of its energy, which is transferred into the vibrational level of the molecule. And then you can ask yourself, how do I have to describe such a process in a Jablonski diagram? Well, what happens is that I have my laser light that excites. This is basically the energy of the photon coming in, and it hits a level here. There is no vibration of the molecule at that energy. It's like a guitar string when I sing at a tone that is not the same as the string. It's very difficult to excite the string of the guitar, so I'm not at resonance. So the process is very enlightening. And then from that level here, I fall down to the excited state of the molecule, the vibrational level. Okay, what this diagram tries to show you is, first of all, the energy of the incoming photon and the energy of the outgoing photon. You can determine that from these distances and the energy level of the molecule. And the second thing that you can read from this diagram is that there is no energy level or excited state at this energy of the photon. So it's a very enlightening process. This diagram shows you already it's very difficult to create this process. And in other words, yeah.
Do the virtual states differ, or you have between your states?
So you mean do these levels here differ?
Yeah.
Well, they're not existent. So what are they? They are, we call them virtual. You know that the vacuum has also energy in it, right? And you can excite an electron out of the vacuum as long as it disappears fast enough. So it's just within Heisenberg's uncertainty. It didn't exist. I think it's a very nice thing. If you look at Heisenberg's uncertainty, you can create an energy package, delta E, for a time delta T, out of nothing, as long as the product of delta E times delta T is smaller than H, Heisenberg's constant. And so in a way, you could look at these virtual states or vacuum levels and interpret them like that. It's not really there, but you can excite it for half a cycle of the vibration. And by the way, there's a Dutch physicist, Casimir. Do you know his name? Oh, so he proved that there's energy in the vacuum. That he did that by creating a cavity, and then if you decrease the size of the cavity, fewer and fewer electromagnetic modes fit into that cavity, and there's energy associated with these vacuum modes, and so he came up with something called the Casimir force. Okay. Long digression from a very nice question. But the point is that this process is unlikely. So it's unlikely to generate the Raman process. So to give you rough numbers, let's say you send 1 million photons onto a molecule. Can I finish my sentence? 900,999 photons will come out at the same wavelength, and only one will be Raman scattered. That's how unlikely the process is. Yes. 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 So there's energy transfer to the molecule, because the molecule ends up in this state, and that's a higher energy state of the molecule. All right, I think it's time for a break. So we'll have a break for like 15 minutes. We start again at 2:30. Is it task balls now? Oké, we maken een opgave nu.
Ja, nu al.
So, you know, now you can buy
Ja, maar voor leer je rustig heel weinig. Ik heb nu bij de stemvariant voor de rest uitrekenen.
I still have like hundreds So I'm gonna give a hint for this exercise to help you out. So the first question is calculate the intensity measured in the detection arm. So the way I would start with this is first write down the field in the detection arm. And so we would like to know the E field in the detection arm, and that E field in the detection arm is of course. Okay. Is of course an E field coming from the sample arm plus the E field coming from the sample reference arm. So I would start with writing down what is the field going back to my sample arm and what's the field going back to my reference arm. And so when you have that, then I'll check it again with you to see if you are approximately correct with these two fields, and then we'll take the next step. Yep. That's simple. Where are the phases? No. and is this in the reference arm? Is this in the detection arm?
En ik dacht dat as a sample reference arm, if you want to.
But how often has it passed through the Lipids? So I want to see the phase of the electric field, and I want to see the path length in these arcs showing up in your E field expressions, and the amplitude coming back from the mirror with the reflectivity of what is it? 1/100.
No, not true.
Ja, maar hij gaat dus als een nieuwe tot dat
Ja, zeg maar. Is dat deze dan?
Moet je L2 keer 2 ja, dat is heel simpel.
Maar met die oh, dat is toch mijn probleem. Deze. Dit is wat je uiteindelijk meet. Misschien weet je dat. Dus dit is basically een soort van. Ja, en dat soort verwerking. Ja. Eerst heb alles uitgelegd. Deze. Stap. Stap.
Dit is dan als eerste van de totale.
Dus als dit zich verplaatst, dan wordt die L2 dan maar dan wordt het wel 2. Ja. Oh, dat is nog wel vertellen. Ja, maar op zich als die LV ja.
Sowieso denk ik dat echt een vreemd is.
Ja. Je lijkt ook niet op mij. Maar dan bij sneller.
Oké, I'll shut up.
Ja, bijna. Wat ik heb probeer klaar te zijn. Nee, en dan komt dat als het van jou is, gooi je direct dat ben je zelf. Ik zei puur voor hoe jij keek. Nee.
Ja, die wordt dan.
Ja.
En dan dat is zo best echt.
Dat is hilarisch. Dat had ik het bij. Ik dacht ook dat ze
Ja.
Het zijn nog 5 minuten. Wat zei je? Het zijn nog 5 minuten. Oh ja. Ja, ik zei ook aan oh ja, maar jij niet ook. Na een half jaar is het
Ja, oh my god. Ik kijk nu al uit.
hey, je moet je ook de clip zien. Als ik hierin ga, lekker. Ja, zijn die reizen mee? Wordt wel de blijfste. Die commissie wordt binnenkort.
Oké, ik ga even beginnen met wat halve antwoorden op de hele vraag. Mag dat niet? Oh, sorry, Dutch. Very good, thank you. So we're starting in Dutch again. So I'm going to give you partial answers now. So we're very interested in this reference arm field. So what is the reference arm field that we get back into our reference arm? Well, the field that is incident on the mirror is E0. And if we take that E0 squared, then we get I0. I0 is the intensity that is incident on the mirror. Oh, sorry, on the beam splitter. So we get first pass through the beam splitter. The question is, how large is the field after the beam splitter? Well, if we look at the intensity, we know that after the intensity, after the beam splitter, BS, beam splitter, we get an intensity that is I0 divided by 2. And that corresponds to an E0 divided by square root of 2. And why? Because if we take that field after the beam splitter and we square it, this squared is equal to E0 squared divided by 2, which is I0 divided by 2. So this is then a very satisfying result, that after the beam splitter, we are left with half the intensity because it's a 50-50 splitter. What does it mean for the field? The field reduces by a square root of 2, not the square root of 2, but the square root of 2. The other important thing that you really need to realize at this moment is that if you look at the fields after the beam splitter, it's not a conserved quantity, yeah? Because in one arm I get an E0 over 2, and in the other arm I get also an E0 over 2. Sorry, square root of 2, square root of 2. So in total I have 2 E0 divided by square root of 2 is square root of 2 times E0. So I get the sum of the fields is larger than 1. And the reason is fields are not conserved. The intensities are conserved. Fields are not. If we do the same math for the field, we get, sorry, for the intensity, we get in the reference arm IR is E0 divided by square root of 2 squared. That is E0 squared divided by 2 is I0 divided by 2. So that is the intensity in my reference arm. I could do the same for the sample arm. And then I get total I0 divided by 2 plus I0 divided by 2 is I0. And that is conserved. So after the beam splitter, my intensities are conserved. Okay. So I'm not going to wipe this out. Thanks. So we're going back to E reference is E0 divided by 2. And now I need a factor for the path that it travels. I want a phase factor. So that is what is the phase of the light that has traveled through that reference arm? It's E I K L R. The phase it acquires for traveling from the beam splitter to the mirror. But it also travels from the mirror back. So I need another factor of 2. So the phase of that field coming back to the beam splitter is I times 2 times K times L R. Okay? So this is my reference arm field. Now I want my sample arm field. Sample arm field. Well, passing through the beam splitter twice, back and forth, gives me an E0 over 2. And who can help me out? How should I deal with the mirror that reflects only 1% of the density? What does it do to the field? So you propose to include that by this. Okay. Sorry? Who said square root? Can you argue why? Yeah, so continue. So your argument is that after the so if my intensity incident on that mirror is I0, then after the mirror I will have an intensity that is 0.01 times I0. Right? That's your argument. And then if I would look at what this means for the field, so I have my E0 incident on my mirror, then I end up with an E0 that is 0.1 times E0, the incident one. Why? Because I take the square of this, then square of this one is I0, and square of this one is 0.01 times I0. And that is exactly the same as here. So indeed, my amplitude decreases by 1/10. When the intensity decreases by a factor of 100, the field decreases by a factor of 10. Okay, so now we have our sample arm field. I'm going to write it as the square root of R. If that's okay with you. That's equal to 1/10, right? Now I need to write my phase, E, I, 2, K, L. L what? S. Okay, so now I have my two fields. I have my reference arm field, my sample arm field. So the total field that ends up in the detector is reference arm field plus sample arm field is E0 divided by 2 I2 K K L R plus E divided by 2 times the square root of R times E to the I to S. Now, if I want the intensity in the detector arm, I need to multiply this one with its complex conjugate, so that is ER times ER star plus ER times ES star plus ES times ER star plus ES times ES. That is my interference term. This is my full terms here. This is IR. This time is IS. And this is my interference term. So ID is equal to ER times ER complex. So this was ER, so times complex conjugate to get rid of this one. This is basically E0 divided by 4. Then ES with ES. This was the ES term. So this is plus I0 divided by 4 times R. Squared and face cancelled. And now I get my interference term. It's E and E0. So that is E0 squared. That is I0 divided by 4 times the square root of R times E to the 2 I K then I get the path length difference between these two. R minus LS. So I'm going to call this delta L plus I0 divided by 4 R. Minus divided to minus 2. Okay, that's still okay in terms of the derivation. You mean in the interference term? No, you don't, because LR is not equal to LS. So you end up with a term that is actually LR minus LS. And because it's in one, it's I2KR LR, this is the reference arm field, multiplied with the complex conjugate of the sample field. So there's a minus, comes a minus in here. The K's are of course the same, but you end up with an LR minus LS. Otherwise you lose your interference. Is this better? Okay, so I can make one more step. That ID I0 divided by 4. I0 plus I0 divided by 4 times R plus. Take this term and this term together to form a cosine. So that is 2 times a cosine. So I get I0 divided by 4 times the square root of R times 2 cosine of K delta L. Okay, so I can take away these 2 and this and make this 4 into 2. I can take the square root of R and make that 1 over 10. And I can take this R and change it to 1 over 100, right? So I have my ID and I'm going to group them together in like the constant terms that are independent of the path length, which are the first 2, is basically it's I0 divided by 4 plus I0 divided by 400. That is these 2 terms, right? So basically it's a quarter of the intensity that I see there. And then if I look at my interference term, that is equal to I0 divided by 20. Times the cosine. So this is my constant term, and this is my oscillating term, right? If I now make a diagram and I look at how what I receive from amplitudes, and I get here I get my, let's say, my constant level, and this is 1/4 of 0. And now I have to draw the amplitude of my interference. And how large is that? Is that interference term now this big, or is it this big? Let you guess which of the 2 solutions is more correct. The small fringes or the big fringes? And in a way, what I want you to calculate is the ratio between this term, because this is my background, and this term. And what is that ratio approximately? Ja, ja, precies. Dat zou goed. Dus dit is het goede antwoord. Hè? Dit is de amplitude ten opzichte van het DC-niveau. Maar wat is het nou precies? Wat is de ratio ongeveer? Ja, ik heb hier, basically, hier staat ongeveer een kwart I0 en hier staat een 1/20ste I0. Dus wat is de ratio tussen die twee? 5. En in procent is dat 20%. Dat is, deze amplitude is 20% van de DC-waarde. Ja. Sorry, did I switch to Dutch again? Oh, I'm so sorry. How long ago? Oh. What I'm trying to say is that the amplitude of the fringes is 20% of the DC value. And I calculate that by looking at the intensity in my detector arm. This is the constant intensity that is independent of the reference arm length. And then this is the oscillating term. And what is the ratio of this oscillating amplitude versus this one? Well, it is 1/4 over 1/20th of the intensity. So that is actually 20%. So now comes I get an amplitude of 20% of these oscillations. 20% of my background. And how large was the reflectivity of the mirror? 1%. So isn't that kind of magic? I get my intensity in the detection arm, and it's basically 1/4 of the intensity. That is basically the reference arm light, and I get a tiny fraction of sample arm light back also. So this is my DC background, and that mirror in the sample arm reflects only 1%. But when I look at amplitude of the fringes it generates, it's 20%. So although the refractor is peak, I get significant. Not small. What you see here is the effect of coherent amplification. That I have a reference arm field that is very large. I mix it with a tiny sample arm field. Due to the fact that these fields are capable of interfering, I get interference fringes that are much larger than my original. Okay, important part of OCT. What we have answered now is question is A. Took us 45 minutes. Sorry? Yeah. Why did you say the intensity is not conserved? Okay. That's a very nice question, actually. But you can see it also, right? Because sometimes it's higher than other times it's lower. And but you also have to remember, if you look at the drawing, if you look at our reflection arm, that there's also like reflected back to our laser. nice thing is that for each interference, when I get the maximum in my reflection arc, I get the min reflected in my reflection arc. If I look at the sum of power, it's going to be that's reflected back to my source arc, that is conserved. So in this way, you get conservative interference. That's nice. There's another way. Energy conservation. You can prove that these two fields should be out of phase. You can have conservative interference at the same time. Which you always like to do. Okay. I think question B is very well doable based on the slides that you've seen. And, actually, you can look it up on one of the slides, or you can do it. And now, so question C. I give you 2 minutes to read the question, and then we can discuss the answer. So drawing that belongs to that pattern is this one. Patterns with zero very large interference. No way that it disappears. Yeah. So what kind of light source produces this kind of interference? That's very good. It's not large. So
we have all things.
multiple wavelengths. Yeah. So
All pairs. It just
so what we need is a low coherent source, a source with a large bandwidth that creates an interference pattern that is localized in space. If I'm looking for another interference pattern, and then everybody except you can tell me what source it is, okay? What is this? What kind of source is that? Sorry? Hypocoherence, yes, monochromatic. Okay, and I'm going to do one more example because I just like it so much. It's a very simple calculation. And it's going to use multiple things that we last week. And it's based on this exercise with this Michelson interferometer. Let's say I have a reference arm, and that reference arm intensity, IR, is equal to 10,000 photons. 10,000 photons. Okay, and I have a sample arm, and the intensity that comes back from my sample arm is 1 photon. Okay, and how does my background intensity look like, or the DC intensity, and how large is the amplitude of the interference? So total I is equal to 10,000 plus 1. And then I get my interference term. And how large is my interference term? How do I calculate that? Square root of IR times IS. That's the amplitude of the interference, right? Does this sound familiar? It should by now, right? It should recognize this. This is the amplitude of my interference term. So how large is this term? This is also equal to the square root of IR times the square root of IS. How large is this in photons? $100. Square root of 10,000 is 100. Square root of 1 is 1. So this is 100. So what I do have, I have an intensity that has a background of 10,000 photons. And on top of that 10,000 photons, I get an oscillation term that has an amplitude of about 100 photons. Okay. How large is the shock noise? So this intensity on my detector. Sorry? How do you get to that? How many photons are reaching your detector? The 10,100, yeah, 10,001 plus or minus 100. Because the 100 is the oscillation. So on average, 10,000. That's the, you said your shock noise was the square root of that, right? So 100, very nice. So I get the shock noise. My shock noise is 100. So what do I see for my signal and my noise? How do they compare? Remember, the signal was my interference term, my oscillation. How large is that oscillation? They're equal. So what does it mean? What does it mean in terms of your signal to noise ratio? Is 1. So I get a signal to noise ratio of 1. And how many sample photons do I get? That's amazing signal to noise. You have 1 photon coming back from your sample, and you're able to measure that with a signal to noise ratio of 1, that's incredible. Why is it equal? Because I've shown that it's equal. Why is it equal? First of all, you have to admire the fact that you get a signal to noise ratio of 1 for already 1 photon. Because I can show you another example. Huh? Let's say I'm not using an interferometer. I'm sending I'm sending a signal into my sample arm, and I get 10,000 photons back from my sample arm. I measure that with the detector. What is the noise? So my signal is my signal is 10,000 photons. What is my noise? Shot noise, in other words. 100. So I get an SNR ratio of 100. With 10,000 photons coming from back from my sample arm, I get the signal to noise ratio that is smaller, right? I get the signal to noise ratio of 100. But I could show for my interferometer, I can come back with 1 single photon from my sample arm, and I get the signal to noise ratio of 1. And remember that this one also suffers from the fact that I have my thermal noise in my detector. So maybe 10,000 photons from my sample arm is not enough to overcome the thermal noise. But if I do it with my interferometer and I am not overcoming my thermal noise, I can just increase my reference arm power. And this signal to noise ratio remains the same if I do 10,000 or 1,000,000. The result of the calculation is identical. I could take 1,000,000 photons here, and then this becomes 1,000,000. This stays at 1. This becomes 1,000 times 1 is 1,000. And my shot noise becomes 1,000, and the signal to noise ratio remains 1. So I can tweak my signal towards this signal to noise ratio of 1 by playing with the reference arm power. And that's why I've shown you last week the diagram. Your sort of noise is a function of reference arm power, and then we have this optimal window. This optimal window, you have a signal to noise ratio of 1 for 1 photon. This is one of the things that helps why OCP is capable of even measuring something from 2 millimeters deep in a lot of these photos have been studied. Okay, it took me a little longer than I expected, so we have 6-7 minutes break. I hope it's okay. And then go back to Raman. So the higher the signal to noise ratio in the direction actually is. Now the better. You want the signal to be larger than the noise. So you want this signal to noise ratio to be higher. Yeah, but here I got 10,000 signal photons. Here I only got 1 signal photon. Let's see.
Ik heb ook niet zo
Oké, wij zaten in de zien ze wel in. Ja, naar de opname. Stuur naar de opname. Nou, er zit geen fout in, maar. Nee, dat weet ik. Ook niet zo als want eigenlijk is het snelheid hetzelfde. Dus signaal voortonen. Snelheid van 10 als 400 signaal voortonen is dat een snelheid van 10. Dat is niet beter, dan krijg je boven de detector noise.
Hey, absolutely, guys. For the
There is a benefit of being here, huh? After all. Okay. So, but let's try and do this. And actually, what do I want to calculate now? I want to calculate. This is my center. It's emitted, and so I have a variation of plus or minus. No, I have a width of that line of about 10 inverse centimeters. So that means I emit light at the edge at 10, 0, 4, and then plus 5. So sorry, that is then 5, 3 centimeters minus 1 and 11, 0, 4, 3 centimeters minus 1. So if I would look at this is wavelength, this is my 905 wavelength. So here's my peak, and then emit a certain width. That width in my energy was 10 inverse centimeters. Now I would like to calculate this width in actual wavelengths with which I measured, right? So now we're going to basically convert these inverse centimeters to wavelength, which is basically 1.05300 and 1 divided by 11.05. Sorry, 430. These are my two wavelengths. So here's my phone. 11.05300. 1 over 9. That is 9. This is 4.7. And this one is 1 over this one. 4. We calculate this one. So if you look at the differences in these wavelengths, it is 904.7 This is 9 of 5.5. So the width of this spectrum, the width of this peak here in my emission spectrum is about 1 nanometer. So that is fairly narrow. If you compare that to how quickly, let's say, the absorption spectrum of blood changes with wavelength, well, that changes over tens of nanometers. And so this tells you now that these Raman peaks are really narrow, really specific, and they're compared with water absorption or blood absorption, and they're way sharper than those. All right. How much time do we have left? I'm in my 3rd hour now, right? And you're kind of tired, huh? Yeah, I know. The rest of it is easy. Because most of it, I think I already explained. And so this is the Stokes and anti-Stokes Raman. So what you see here is a Jablonski diagram where we go from the ground state to that kind of virtual state. And from that virtual state, you can go back to the ground state. This is the Rayleigh scattered photon, or just normally elastically scattered. And then you can go to these excited levels in the molecule. Let me see, what's the second one? Here is what we call the anti-Stokes process. Here we have a molecule that's already excited, and then it goes to a virtual state and it falls back to the same excited state. So basically, this is your standard Rayleigh scattering. But the other possibility that you have here is that you, from this virtual level, fall down to the ground state. Now, the photon that you emit, it's a larger energy span, so it's a shorter wavelength. This is the Jablonski diagram for anti-Stokes scattering. It could be thermal excited. So it's like the gas molecules bouncing against one another, and they also can, just the collision of molecules can also generate vibrational levels. So that's associated with temperature. So you can describe always the occupation of an excited state over the ground state, that ratio, by a description that's by Boltzmann, that says that the ratio of these two states is e to the power minus the energy difference between the two divided by kT. And this is the thermal excitation of the state N1. And to give you just a feel for this, this kT is about 200 inverse centimeter at room temperature. So that means that if you look at the Raman spectra and you look at the area up to, let's say, a shift of 200 to 300 inverse centimeter, we can look at vibrational states that are thermally excited at room temperature. So it is expected to see an anti-Stokes signal. And so this is then an example of sulfur. Here at 0 shift, this is your elastically scattered light. Then we go to the Stokes side, and here you have excited the vibrations. You could see vibration at the what is it, 160, and there's one at 210, and there's one at what is it, 480. If I go to the anti-Stokes side, I can see the around 160 is this one, and the 210 is this one. I can see them because they're about thermally excited. But the one at 500 is really small because that has barely any thermal excitation. So this is typically what you expect for a Raman spectrum. You get the Stokes shifted signal and the anti-Stokes shifted signal at the room temperature. Okay. Then the probability of this Raman process. So if you look at the near infrared scattering in tissue, then the length before a photon gets scattered in tissue is about a millimeter or a tenth of a millimeter. That's, you can express it as mu s prime. If you look at the absorption of near infrared light in tissue, it gets absorbed at about 10 centimeters of propagation distance. If you look at the absorption of red wavelength in water, that's about 5 meters. And so if you go diving, how deep do you want to dive? You go through the beauty. You see beautiful colors down there. So how deep should you go 30 meters? Anybody? No, and why? Yes, so it's a gray world. It's a gray world. Why would you go that deep, right? It's better to stay within the first 3 meters. The colors are much better. So 5 meters for red. The Raman process, the likelihood of a Raman scattering process in water, a photon has to travel 3 kilometers in comparison to the other lengths here. So you see that the likelihood of a Raman scattering process in water is really small compared to all the other processes. This is why the Raman signal is so weak. It's really weak. Like 1 in a million photons get converted or less. So you can you have had scattering cross section, right? How that relates to something. So I can give you a number now that the Raman scattering cross section of a molecule is on the order of 10 to the power minus 30 square centimeters. So not much. Or 1 in 10 to the power 8. That's actually 1 in 100 million photons are scattered. So this is the downside. So the beauty is very nice, rich featured spectra, but the signal is so weak. So like it says here, it is a weak, low probability. So it requires long exposure times or high concentrations. With the laser, you can, up the power of the light source significantly to help you out compared to the sunlight they were using before in 1960s. And it has a wide range of applications, chemical analysis, geology, process analysis. The car industry, they used it to examine the combustion process. Like Raman tells you something about temperature, right? So they used it to monitor the temperature inside an engine without putting a thermometer in there. And archaeology and biomedical optics. Okay. If you look at the intensity scales as the frequency to the 4th power. So the laser power will depend on absorption and photo damage. That's the intensity. The alpha is the polarizability. And so if you look at the infrared signal, it is proportional to the wave factor. The incident intensity, the polarizability squared, and the frequency of the light to the 4th power. So that means that if you use shorter excitation wavelengths, so that is higher frequencies, the Raman process is more likely. Nevertheless, long excitation wavelengths are more commonly used, and that's because you get no fluorescent background. And I think that is the next slides I'm going to show you. So the Raman processes, as I've shown it to you so far, is that you go from a ground state, you excite to this gap here into no man's land with the photons. But let me see. I can, of course, use a shorter wavelength, but that also brings me in the region of the electronic excitation. So I basically start to excite electrons. And what can happen with the electrons is that, oops. Oh, I was hoping for this slide, yes. So when I look at the electronic excitations, I can also, use it and fall down to the ground state again. I get a Stokes shifted photons, but I also can have an relaxation, electronic relaxation in the molecule, and then I get a fluorescent process. So I get also a photon that's coming out of a longer wavelength, but it's fluorescent. It has nothing to do with the Raman process. And now the problem is that this is again, this fluorescence is a process that's much more likely than the Raman process. So it quickly overwhelms. So this is actually this is the worst version of the fluorescence, because if you look at this fluorescence, the wavelength of that fluorescence is very similar to the wavelength of the Stokes shifted photons. This is the worst kind of fluorescent background that you can get. So this is called UV resonant, very short wavelength. The fluorescence is actually shifted, is significantly different from the Stokes shifted light, so this can work. The downside is you use a wavelength of shorter than 300 nanometers. So in general, you're in the area of DNA damage. So this is not something you can use in vivo. 314 is a wavelength that you start to directly damage DNA with light, so you want to stay away from that. Then, of course, you get the visible excitation. Very nice, but we get this background. And then we go to the near infrared, we excite in this gap, and we don't have the background fluorescence. So that's the big advantage of going here. For that material, archaeology, and if you want to explore Mars, it's of course fine to use this here. Well, all the benefits. What am I going to do now? Okay, I'm going to show you a few examples. This is, for instance, the spectrum of glucose. This is lactic acid, and this one is creatinine. It shows you, let's say, the different Raman spectra. And this is, for instance, if you want to do a blood analysis, you take a sample of blood, you collect the Raman spectrum, and then you want to get the fractions of these molecules out of your Raman spectra. So basically what you try and do then is you measure one spectrum, and you try to deconvolve that spectrum into the base spectra of these fundamental molecules in the sample. And well, people spent a lot of time on it. Actually, I think last time I already decided to not show much of that, but it's doable, but it's painful. Let's look at another one of the difficult things with Raman spectroscopy in the biomedical optics, and that's the fact that you have to use excitation and detection fibers that are different. And in the next slide, I will show you why. This is the spectrum that comes out of the fiber that when you send in a single wavelength. And so these are the shifts, right? So you look at 250, it's a tiny shift from the original wavelength. But what you see is that fiber itself creates a tremendous background, Raman background. And so you can imagine that if this is already the spectrum that comes out of the fiber, how are you going to measure the very weak signals from the tissue itself? And because the fiber that you use can be 2 or 3 meters long. So over a length of 2 to 3 meters, you get Raman processes in the fiber that generate the spectrum like this. And then you get into tissue. Now you have to make a millimeter or 2 through tissue. That's where you get an additional tissue signal. That is what you collect with the fiber, and that's going to be then completely hidden in this way. So using the same fiber for excitation and for detection of a Raman signal in tissue is virtually impossible. So you need to go to more complex geometries where you use your excitation fiber. Then you have to filter out all the light that's not your excitation light. You want to get a very clean, narrow wavelength out of your excitation fiber, and then you're going to collect your light in collection fibers that are basically then positioned around the excitation fiber. This filtering process is really key for successful Raman measurements in tissue. You really need a transmission filter for the excitation fiber that looks like this, really narrow, only transmitting the excitation wavelength, and then for the detection fibers, you actually want to block out all excitation light that comes back from the tissue, because even that excitation light traveling on the way back through your fiber generates a Raman signal. So even there you want to get rid of it. So you want to filter for your detection fiber that cuts out all your excitation light and only transmits your Raman shifted signal. And this is what makes in vivo Raman spectroscopy so difficult. The fact that you need to put a lot of effort into proper suppression of these first of all here of Raman signal generated in the fiber on the way to the tissue, and here eliminating excitation light from the tissue to the detector. I'm tired also, so it's yeah, I'm going to do one more topic, that is cars, after the break. And so basically what I'm showing here is again, this is a Raman spectrum collected from a non-atherosclerotic artery and from a non-calcified atherosclerotic plaque and from a calcified atherosclerotic plaque. So twice this kind of thing. I think you're familiar with a heart attack, right? Who knows what it actually is? What happens during a heart attack? Sorry? Yes, and why does that occur? So you get an occlusion, but I mean, if I have an artery, you know, where that slowly kind of gets narrower, narrower, do you think that would create a heart attack? So how do you generate the blood cells? Multiple ways. Multiple ways, yes. But in a heart attack, it's the following thing. What happens is you get your arterial wall, and below that arterial wall, you build up a pool of lipids. And those lipids are thrombogenic, which means that when they are released into the bloodstream, they create a blood clot. So the molecules in the blood react to this lipid to, you know, this to form a stolsel. It helps me out in English here. The thrombus creates a thrombus, yes. So and this is an acute event, right? So when you have that lipid pool in the wall of your artery, and that wall breaks, it releases that lipid in an acute event into the bloodstream. It immediately creates a clot. It immediately blocks the bloodstream in that area, and that's where you get downstream. You get the lack of oxygen. And so this happens in coronary arteries. So what are coronary arteries? These are the arteries that supply oxygen to the heart itself. So it's like the oxygen to the engine, so to speak. And so when that's interrupted, that you know, creates serious problems. So what are now non-atherosclerotic artery? A non-atherosclerotic artery is an artery that doesn't have this lipid pool in it. The non-calcified atherosclerotic plaque is a location where you have a lipid pool, but it's underneath a cap that is non-calcified. So it doesn't have any calcification, And you have, this is a Raman signal of an artery that's underneath a calcified cap. And so in coronary diseases, they make a distinction between these non-calcified and calcified plaques because there's a difference in the risk that they rupture. And don't, hold me to it, but I think that the calcified plaques are more dangerous than the non-calcified plaques. And so knowing what the plaque type is important because then you can assess the risk of that particular plaque or lipid pool, and you can decide which one you will try to strengthen with a stent. So you now understand the importance, and then this is then the signal that you get for these Raman signals for these different plaques, and you can see that they're really different. So you could see that this is potentially a promising way to characterize plaques in coronary arteries. You have to realize that this is not in vivo. I think this was ex vivo. So you can understand that since the Raman signal is so weak that you might need to integrate for longer times. And so, doing this in vivo still have significant hurdles, but it shows the promise of a technology like this. Okay. So before I go into cars, we're going to have last break, and I'll try and keep it light. Mm. 15 minutes, that's official. So if you, so what I'm going to explain now is that if you have a process that you can do with one photon, why don't you do it with 3 photons? Well, because it's much better. And so this is cars. The idea of cars is that I take a photon that excites to my virtual state, but at the same time, I provide a photon that matches from the virtual state to the first vibrational level. And you can think of this process as what happens in a laser, right? You stimulate emission from an excited level down to the ground level. So basically what you do is with this photon, you excite to here. With the second photon that you supply, you excite from here to here. And with the third photon, you excite from the excited up top. And then from this one, you go down to the ground state. And what is the result of this whole process? It's an anti-Stokes photon. It's a photon of shorter wavelength. And why is it beneficial to have a photon of shorter wavelength? Because that's all the fluorescence processes and Raman processes and things that generate the background, they all generate the background at a longer wavelength. But if you have a method of generating a signal at a shorter wavelength, you have a beautiful way of filtering out all non-relevant and disturbing background signals. So that is the advantage of cars. Coherent, coherent, anti-Stokes, because we're looking at the shorter wavelength emitted photon, Raman spectroscopy, or cars. And if you look up in the literature, who published the first cars paper, it was a research group with General Motors. So it's a very appropriate acronym. And they used it to study the temperature in their engines, like I said before, that with the occupation of the excited levels as a function of temperature, you can study combustion processes. That's what they used it for. Okay. So it's more sensitive or stronger than spontaneous Raman. That's because of that stimulated part of the process. It has good contrast. The signal is at a higher frequency, so we get minimal background interference. But it has, of course, one downside. No, it's not true. What you need to do is you need to provide a photon that matches this transition, right? So you basically only become sensitive to one vibrational level in your sample. With standard Raman spectroscopy, you send in one wavelength and you measure a whole spectrum. You can measure all vibrational levels in the molecule. With this technique, you target one specific vibrational level and you're looking at the strength of it. Why do you pick one particular? Because you provide two photons and the energy difference of those two photons need to match the vibrational energy of the molecule. So that's the downside of it. And to give you an idea of why does this work, so the idea is that you have your pump photon and your Stokes photon. That's the one that fits. That fits exactly here. If you look at these fields and you would offer them at the same time, and you look now at the beating between these two frequencies, the beat between these two signals is exactly your vibrational level. So this is another way of or to visualize or make acceptable or have you being more convinced that with providing these two wavelengths, you have a higher probability of exciting the vibrational level of the molecule. And the reason is that if you look at the envelope of the beating, the envelope of the beating is exactly at the frequency of the vibration of the molecule. I just explained this. I'm not going to go into details here and here. I want to go to a process that actually has become a more dominant way of doing the same thing as what cars is able to do. So the advantage of cars is that it provides a better signal, higher signal than just Raman. What I'm going to show you here is stimulated Raman scattering, and it is a process that has the same benefit as cars, but it's simpler to implement. So what you do is you provide both the pump and the Stokes simultaneously. And so what you do is you basically try to get the molecules in the excited state, right? That's what happens in this process. But what you can do is you can, oops, this should be an animation and it's not. What happens? Oh no, it is. Damn it. Sorry? Which graph? This one? I'm trying to figure out what's happening. So what I'm trying to explain in this graph is the following, and let me check if it's right. Which one is chopped? That can work. Okay. Yes, I remember. Sorry that it took me so long. So this is an example of a Raman spectrum that is here in inverse centimeters. And what we do is we pick one particular resonance out of this spectrum. Let's say we look at the 1500 nanometers, inverse centimeters. So that means that take two beams where the two beams have an energy difference that exactly matches the speed here. And so what I can do now is I offer these two beams simultaneously in the sample. What will happen now is that with this beam I will excite, and with this one I will stimulate down to this level here. The thing is that this stimulation down is basically an amplification process, right? So I get my excited state and I go down, so this one becomes stronger if this resonance is present. If this resonance is present, this signal becomes stronger. And if I look at my pump beam, if this resonance is present, this pump beam gets weaker because there's a little bit of energy transfer from the pump beam to the Stokes beam. If this resonance is not there, then my pump beam will remain with the exact same power, and my Stokes beam will also remain at the exact same power. If this resonance is present, I get a transfer of energy from my pump beam to my probe beam. So this will happen, right? And so what I can do now is I can measure the intensity of my Stokes beam, the fluctuations in the intensity. I can look at the intensity of the Stokes beam, or I can look at the intensity of the pump beam. And when this resonance is present, the intensity of either the pump or the Stokes beam will change. And this is something I can measure, and that is now my signal. This is called the stimulated Raman scattering setup. Actually, it is easier to operate than the car setup. So this is why, this is the kind of microscope we built. And just to show you one example of what you can do with it is we looked at the zebrafish. And zebrafish have a fat storage. And what was done with these zebrafish is they were put on different diets to see what their fat storage is doing. And they were put on their circadian rhythms were disturbed, which means their day-night rhythm were disturbed. And we looked at what it does with the fat storage. So we're looking at lipids. Lipids have a very nice strong Raman signal. So this is what happened with the adipocytes in the zebrafish with a normal diet and a high-fat diet. That's not much of a surprise that with the high-fat diet, you get a much larger prevalence of much larger amount of fat stored in the fat storage. This was on a high glucose diet. And this is the way we analyzed it. So we take we take an image of the zebrafish, and because we're looking only at the lipids, we look at the Raman transition in lipids. We only get signal from the lipid region, and we can calculate the sizes. I think, oh, this is the end. Okay, then in words, I have to tell the other one, which might be really important to students. That is when you take these zebrafish, and you feed them the same diet, and with one you leave them in a normal day-night cycle, and for the other one you disturb their day-night cycle. Or for the disturbed day-night cycle zebrafish, the fat storage increases. So it shows you that regular sleep pattern is actually very important for your overall health and your metabolism. And I think that's a good last message of my lecture.
Maar dan moet ik wel. Ik heb een korte sessie.
Een vraag over zo'n Raman Spectroscopy.
Vind je het erg? Volgens mij nemen we nog op. Dus ik probeer krampachtig om de opname uit te zetten, maar dat lukt niet. Ik weet niet als ik nou...
Stop recording.
Waar is dat?
Nee, dat is pauzeren en stoppen.
Oh ja, pauze. Stop.